All right, so welcome to 3.2, plot linear functions. All right, so let's evaluate these expressions. These are expressions in x equals 3. So 2 times 3 minus 1, right, is 2 times 3 is 6. Multiplication before subtraction, 6 minus 1 is 5. Negative 4 times 3 plus 2. Negative 4 times 3 is negative 12. Negative 12 plus 2 is negative 10. This one is 3 times negative 2 plus 5. So it's 3 times negative 2, negative 6. Negative 6 plus 5, negative 1. 5 times negative 2 minus 3. 5 times negative 2, negative 10. Negative 10 minus 3, same as negative 10 plus negative 3, negative 13. All right, so that was evaluating an expression. All right, what we're going to be doing is plotting a function. All right, and so these are not going to just have x in them like expressions. They're going to have y in them and x, and they're going to be equations. They're not going to be expressions. So let's see that. So a function is made of inputs. X is what you put into the function. Y is what you get out of the function. It's always that way. And together, inputs and outputs create ordered pairs. So let's see that. So it says y, this is our first linear function, or function. And this is a y equals 6x minus 1 is the function. So, right, 6x minus 1 by itself would be an expression, but this is a function. It has x and y. And we're going to put x into it. So that's our input. And you do the exact same work as an expression, though, right? You put x into it, and you do 6 times 2 is 12, minus 1 is 11. Instead of writing 11, you write y is equal 11, and that's our output. It is that simple. All right, try that one. So our input is 12, and then you do 1/3 of 12, and our output is y equals 4. Our input here is negative 7. And our output, negative 14 plus 3, our output is negative 11. So notice these are called functions. And this function is y equals negative 5x. And this one, the input is 0. And the output is also y equals 0. A linear function, I mentioned this in the last screen by mistake, is a function where the exponent of x is 1. So only one of those, they're both functions, right? They both have x and y, and there are other rules as well, but they both have x and y. And but which one has an exponent of 1 for x? Well, this one right here, we don't write it, but that's called a linear function, okay? And pick out the linear function here. So once again, the exponent of x there is 1. We just don't write that one. And this is a linear function. What does that mean? It means it's going to be a line when we graph it. Things are going to come out in a straight line. These other two are functions that we're going to graph later. This one, you don't have to know this yet, but later in the year you'll learn that this is a quadratic function. And this is a, right, and because it's x squared, and this with a x cubed is a cubic function. But we're doing linear right now. Okay. All right, so we're going to do multiple ordered pairs. And so when you have multiple inputs and outputs, that's where these t-tables that look like the letter T come in handy. So we're going to evaluate y equals 4x minus 8. So typically we would write the actual function so that they're not symmetrical. The y side is usually bigger than the x. And that's so if you need to do any work, you don't do it over on the side. You do it right in the t-table. So say, right, you could do 4 times 1 minus 8 in your head, but if you couldn't, or you don't want to, you do 4 times 1 right there, which is 4, minus 8 is negative 4. And there's our output, negative 4. You don't have to circle it, though. And then we do the input of that is 4 times 2 is 8, minus 8 is 0. Then 4 times 3 is 12, minus 8 is 4. 4 times 4 is 16, minus 8 is 8. And 4 times 5 is 20, minus 8 is 12. Okay, evaluate this linear function, right? These are both linear functions because the exponent of x is 1 there. And so We write it right here, right? If those who don't have the printout, you make your own. It's not that hard. Just like that, and you fill them in, right? So the first one I went 1, 2, 3, 4, 5. Here I went 0, 2, 4, 6, 8. And so half of 0 is 0 plus 3 is 3. Half of 2, all right, since I'm doing a half, I made my life easy and went with even numbers. Half of 2 is 1 plus 3 is 4. Half of 4 is 2. 2 plus 3 is 5. Half of 6 is 3 plus 3 is 6. And half of 8 is 4 plus 3 is 7. Ooh. Now, one of the things you're going to notice about functions is this. Notice there's a nice little pattern there, 3, 4, 5, 6, 7. And there was a pattern here, right? Even numbers going up by 2. If there's a pattern in the domain, the x values, there will be a pattern in the range. And there are different patterns all the time, but there are patterns. So here we had a pattern in the domain of going up 1. Here we had a pattern as well. We went up by 4s, right? Each number is 4 bigger, right? That's helpful when you're doing this work, right? Say you got 3, 4, 5, 9, 7, right? 9 wouldn't fit the pattern. You made a mathematical error, right? So you can check your work that way. Are you following the pattern? Can you use that to do shortcuts as well? Yes, you can. Okay, so we're going to plot our very first linear function here. So y equals 4x minus 8. So we're going to make a t-table, and we're going to put x on the left, and y on the right, and y equals 4x minus 8. Now I feel like we just did this one, so let's just make sure. So I'm going to pick 0, 1, 2, 3, 4, okay, and then 0. 4 times 0 minus 8 is negative 8. 4 times 1 minus 8 equals negative 4. 4 times 2 minus 8 equals 0. 4 times 3 minus 8 equals 4. And 4 times 4 minus 8 equals 16 minus 8 is 8. So there's our ordered pairs. Now, we're going to, for those who don't have the printout, you're going to make your own. So you're going to draw a y-axis. You're going to draw an x-axis. You're going to label x and y like that. Okay. Now, we have 0, negative 8 right there. Then we have 1, negative 4. We have 2, 0. We have 3, 4. And we have 4, 8. Now, when you have the grid, it's nice and easy. For those who have doing a sketch, it's 1, 2, 3, 4, 5, 6, 7, negative 8. Right? Try to make them equally spaced. Then 1, 1, 2, 3, negative 4. Then 2, 0. Then 3, 1. Oh, that's, I want to make it evenly spaced. 1, 2, 3, 4. And then 4, 8. 5, 6, 7, 8. And then we're going to draw a line in between that doesn't really connect the dots. It's through the dots. All right, and so let's do that. I'm taking a ruler, so we needed a straight edge. And sorry if I didn't tell you that before. So I take a ruler. You can pause the video and go get a ruler if you need to. And there is our first linear function that we drew, right? And you'll know here's one with a sketch, right? It's not going to be quite as accurate, but it's fine, all right, without the grid, all right? And so we've plotted our first linear function. Now, please, we plotted 5 sample points. There's a point, right, where x is 100 and y is 4 times 100 minus 8, which is what, 392, right? There's that point somewhere. And that's how we show it with that arrow. So look at your graph. Did you put an arrow there? There's obviously one down at negative 100 as well. There are also these points with fractions. All along here, there's an infinite amount of points, including decimals and fractions. We could plot those. We could put in, if you really wanted to put 4.1 in there and do the math and try and graph it, you could. But it's way easier to plot the whole numbers and just draw a line through them and then realize all these other points are along that line. All right, and that's called a linear function. All right, so let's plot our second one. And this is the second graph that we did, right? So here's x was what? We used 0, 2, 4, 6, 8, and y equals 1/2 x plus 3. So 0 is 3, the 2 was 4, then 1, 5, 6, 7. Those are our points. So we have 0, 3, we have 2, 4, we have 4, we have 2, 4, then we have 4, 5, then we have 6, 6, and then we have 8, 7. There we go. All right, so I want everyone to put, say, -10 in there. So what's half of -10? Half of -10 is -5. And then let's add 3 to that, and you get -2. So it goes -10, -2 is also on this line. So we take our straight edge, our ruler, okay, and so we are going to draw a line through that, and we have our linear function. All right. Now for those doing the sketch, let's just do that. Yeah, be careful here. I messed up my sketch the first time I tried to do it. Remember, that one's not that neat there. I missed 0, 3. All right, so 0, 3, 1, 2, 3. Then 1, 2, 4. Then 4, 5. Then 6, 6. Then 8, 7. All right, and for you guys to try to put this one over at 10, -2, it's going to be a little trickier, right? Because you're not going to be as, without the grid, it's not going to be quite as accurate. But you have the idea. That's the function, linear function, y equals 1/2 x plus 3. All right, so this is another kind of table. And so we're going to fill this in. Now, if you don't have the printout, you're going to make your own table, right? It's not that hard. And right, you write x and y, and you fill in -4, -2, 0, 2, and 4, like that. And you'll notice on a T table, x is always on the left. On this kind of table, this is called an input-output table, where x is the input. The input x, right, is always up top, always. And the output is on the bottom, okay? And so let's fill that in. So when x is -4, y is -1. Now, what's not, T-tables are nicer because you can do your work right inside them. But here, you're going to have to do it on the side if need be. -2 plus 3 is 1, 0 plus 3 is 3, 2 plus 3 is 5, 4 plus 3 is 7. So there's our point. So the first point we're making is x is -4, y is -1. Second point is x is -2, y is +1. Third point is x is 0, y is 3, x is 2, y is 5, right there, and x is 4, y is 7 is right there. I think that's, oops, my 2, 5 got erased, and that's far enough. Now, you don't make it just the length of those dots. You go all the way through them to past the edge of the grid to show that this linear function goes on forever. Okay. All right, so please take these notes, they're very important. A linear function contains an infinite amount of points. All right. The domain and range, the x values and the y values on a linear function are usually all real numbers. What does that mean? Are there numbers that are not real? Yes, there are. We're going to talk about those later in the year. But so far, all you know about are real numbers. All right? There are a thing called imaginary numbers. But all real, so x could be any number, right? From -1.5 million to 5 billion.007, right? It can be any number, and y is the same. And so we show you the domain and range are not what you see here, all right? Not what's in the table. The domain and range are all real numbers, okay? So here's the one you just did. And so I want you to list 3 more points along the line, all right? Well, here's one, -6, -3, right? That's not in the table, but it's on the linear function. Here's one, -9, -6. Here's another one. Here's 1, 4, right? X is 1 wasn't in the table, but it's a point on the line. There's also a point right there at 1/2, right? X is 1/2, right about there. X is 1/2. And if you follow that pattern, I think X is 1/2, Y is 3.5. That's a point on the line. There is an infinite amount of points. Now you could choose other ones, right? There's ones over here, okay? Off the grid as well. There's an infinite amount of points in the domain and range on a linear function. All right, so now there's a point, the 0.59. Now, if it's on the line, it works or makes this true. So check, put those points in the right spot. Put the X where X is, put the Y where Y is, and see if it makes it true. If it does, it's one of the infinite amount of points on the line. Let's see. So 9 is the Y coordinate, right? And 5 is the X coordinate, because it always goes that way. And so we have 9 equals 3 times 5 is 15, and 15 minus 6 is 9. Yeah, so this point was a point on the line 3x minus 6. So even without the graph, you just put it in the equation, and you can tell if it's a point on the line. Try this one. So this time the Y coordinate's 8, and the X coordinate's -1. So 8 equals -3 minus 6. 8 equals -9? No. All right, so this is yes, by the way, is the point on the line. All right, so there's an infinite amount of points on the line. There's also an infinite amount of points not on the line, okay, right? All the other, right, if the line is like this, right, there are all these points that are not on it, but there are also all these points that are. And this is how you check when you don't have a graph. Okay, so let's practice. Let's plot this linear function. All right, you're going to make a t-table. You're going to fill it in. 0 times 3 minus 2. 1 times 3 minus 2. 2 times 3 minus 2. 3 times 3 minus 2. And 4 times 3 minus 2. So there's what I've got. So I have 0, -2, 1, 1, 2, 4, 3, 7, and 4, 10. Okay? Now, on the homework tonight, I get some people, right, who get graphs that look like Z's and things. No, they all come out in a straight line. If it comes out in a Z, you messed up. You erase it and you fix it. Here we go. Right, nice long with arrows always on the end. On the tests, I take points off for people not putting their arrows on the end. What are the domain and range? Not these things. It's not yesterday. Right? Yesterday, you were plotting a bunch of individual points, and so the domain was just what you saw on the table. Today, the domain is all real numbers, and the range is all real numbers. Right? X could be anything from 1,000,000 that way to a -2 billion this way. Y could be anything this way and this way, plus all the fractions and decimals along the line. All right, is that point on the line? How do you check without a graph? Yes, I put 2 no's. I do that, by the way, because there's always a student who thinks if one is no, the other one has to be yes and doesn't do his work. So I thwart that. So often it will come out no, no, or yes, yes. So which of these is linear? This one. Right? And when that graph, what does linear mean? What does linear mean when it's a graph? It means it's going to be a straight line. And you actually don't have to say the word straight in algebra. All lines are straight. This is not a line in math. That's a curve. Okay.